Okay, here we are to part 2, and I just want to start out where we left off. The last two we covered yesterday were these two, the exponential function, natural exponential function, and the natural logarithm function. And these two are inverses of each other. So that's one of the things we're going to be talking about later this year. Next, the next function we have is called the sine function. And this is it right here. So, is this function going to be odd or even?
Odd.
Even. Neither. Mr. Jerry, you want us to write this right now?
Yes, I'll make a little sketch like you did yesterday. By the way, that was, actually that was very beautiful what you did yesterday for your notes. I have to say that. And this is going to be an odd function. Right? And what is the definition of an odd function? Well, here it is. It's going to be f of negative x is going to be equal to negative f of x. So here we have this point here. F of x is the same as negative that is over here, down here. So you're going to get this kind of rotation. Okay, what is its domain? All real numbers. What is its range? Yeah, negative 1 to 1 is how we say it there, right? Negative 1 to 1. Do we have vertical asymptote? None. Do we have a horizontal asymptote? No, we don't actually. And we'll talk a little bit more about that in a minute. Do we have boundedness?
Yes. Above and below.
Yeah, we call this bounded above and below. So we usually just call it just bounded if it's bounded, if the function is bounded both above and below. And end behavior. End behavior, limit as x approaches infinity of f of x. As x approaches infinity, what does f of x approach? 0. No. Yeah, there is none. So does not exist. So we say that instead of equal, say does not exist. And this is usually when limit does not exist, it's positive infinity or negative infinity. Here you have oscillation. If the thing oscillates and doesn't hone in on, and when angels set 0, if this thing did shrink, sometimes you'll see these things like this, that it will go like this and gradually kind of shrink like this and gradually go to 0 like that. You can see it like that, but in this case, not. So, and again, also limit as x approaches negative infinity of f of x does not exist. Now, can any of you think of real world uses for this type of function? What did you say? Waves. So you kind of look at it sideways, looks like a wave pattern. What else?
Heart.
Regular rhythms of heart, yes, could be modeled with this kind of a regular up and down. What other thing do you notice that goes up and down in more or less a regular pattern? Yes. Okay, weather, temperature, right? Day to night temperature, tides, the length of the day will go to a point. Anything that goes down to something and comes back up and repeats can be somewhat modeled using a sinusoid curve. Now, what I'm going to do is quickly show you the next one, which is the cosine function. Now, it's almost the same thing, but cosine means, what cosine means, it means the complement. Complement of sine, that's what it means. What does complement mean? What does complement mean? You might have learned that in geometry class. What is a complement? What is a complementary angle? What is a complementary angle? Adds to 90, right? So what this is this is 90 degrees. The cosine is we're going to talk about trigonometry more next semester, but it's the complement of the sine. And so the sine is like this, right? And so the thing is just shifted. So it's just shifting. And this, in all respects, is the same as sine, except for what? Is this thing even or odd? Even. And so for this function, the only thing that's different is odd versus even. Every other attribute is exactly the same. Okay? And so you can just write down everything else same as sine right here. Okay? I don't want you to spend a lot of time writing for this one. Are you okay on that?
Wait.
Everything else same as sine. Okay, let's go on to this next one here. We have the absolute value function. You remember in Algebra 2 honors we did this one last year? Remember that one? And so is this one here going to be odd or even? It's going to be even. What is its domain going to be? All reals. What is its range going to be?
0 to
And vertical asymptote? None. Horizontal asymptote? None. Bounded?
no.
Below, yes. In behavior?
X approaches infinity. F of X approaches infinity.
And limit as X approaches negative infinity, f of X also equals infinity, right? So really, that's it. Now, what would you use an absolute value function for?
Something that can't be true.
Something that can't be negative, and we did talk about this in Algebra 2 last year. What cannot be negative? Distance. I mean, just absolute value of distance, how far apart things are. So it actually has more uses than you think it would. You could use it for, and some of the things we went over in Algebra 2 last year. All that. Okay. All right. Now this one here is called the greatest integer function. So, you ever seen that one before? Is this one going to be odd or even? The thing looks like it's odd. It looks like odd, but it really is neither. And the reason you can tell is that if we take this one right here, this point, here would be 2, 1, right? Well, if this thing was really an inverse function, we would have -2, -1, right? Do these things reflect here perfectly? No, it doesn't. So it kind of looks like an odd symmetry, but not exactly. So it's kind of strange like that. The domain, all real numbers. What about the range? Yeah. So here's the way I would write the range. So I'm just going to do this pretty quickly. I'm going to put ... -1. And actually I'm going to put union here like this. U for union, 0, union, 1, ... So that's going to be our range. Pretty weird. Okay. Yes. Okay. Now, see, vertical asymptote, none. What about horizontal asymptote? None. What about boundedness? No. Bounded, no. What about limit as x approaches infinity of f of x equals infinity, and limit as x approaches negative infinity of f of x is equal to negative infinity. Now, can you think of real world uses for this type of function?
Things that can't be fractions or decimals?
Yeah. Things that cannot be fractions or decimals, that's one thing, right? If you can have a full integer thing. Can you think of a specific use of such a thing? This thing is used a lot more than you think it would be. How much does it cost to mail a letter that's less than an ounce? Does anybody go to the post office anymore?
Stamp?
Like a stamp, the basic first class post. How much?
10 cents.
No, that would be back in like 1990 or even earlier.
I have a question, serious question.
Yes.
What do we actually get from learning this stuff, like in actual life? Because like none of this stuff I can like relate back to life, so I don't even know.
Okay, now, do you remember yesterday that I asked the question, what could this be used for? Did anybody else remember what I said, what could this be used for? What do we use quadratic functions for, and what did I say? Satellite dish. Remember we talked about satellite dishes yesterday? Yeah. Did we talk about private? So,
What does it have to do with that? Yeah.
pardon me?
What does that mean? Like, how does it relate to that?
That's the shape of a parabola. I'm referring to yesterday. So what on each one of these things, I've been taking special time out to ask, what is the real world use of this?
But like, if it just looks like it, that's not really like relating it, like
Okay, we talked about sine functions and cosine functions, right? How they could be used to model. So what happens is we're looking at parent functions that we can alter to model real world uses. Every one of these things has a real world use. And we've talked about this generally, but part of the precalculus is where we actually are going to do that. But on a broader aspect, some of the things we do, it's going to be hard to directly see real world uses. What happens is you're trying to get ready to go to some place in a career or in academia, whatever, where you're going to need to have a bigger toolbox of analytical ability. So part of what we're doing here is building that ability up. And so not everything that we see is going to be, we can deem as directly applicable. Now this thing right here, we talked about postage stamps, right? So what happens is that up to 1 ounce, it's going to be 55 cents, right? So 55 cents. And so all the way up to 1 ounce, and then after you go to 1 ounce, what happens? You go up to 80 cents or whatever it is. And you have another thing here. So in commerce, when you go to a gas station, you pump gas, it goes what? Penny by penny.
That's just basic multiplying.
But it still uses this pattern. It uses this step pattern. So a lot of these things have more real world use than you think it will, and the next one we're going to come to is a big example of it. This is one that is kind of at the back of a pre-calculus textbook that people don't think about very much, the logistic function. But this one probably starting March of this year became maybe the most important type of function in the world. Had to do with coronavirus. Because what happened was, when we started out in talking about the coronavirus, they were talking about exponential behavior, right? They were talking about this, about days to doubling. But I don't know if you watched any of the press conferences where they had the epidemiology experts, Dr. Fauci and Dr. Birx. And Dr. Birx continually talked about going to the logarithmic phase of the curve. And what happens is eventually an exponential function will do this. Why in our real world would an exponential relation not continue on forever?
Because there's a limit.
Because there's a limit. And what would be the limitation, say, for something like coronavirus? Yeah, limited number of people. So limited number of people to infect. And so we don't know exactly where we are, but this thing right here that has become like never before a real world use of this type of function. So this is one thing that is relevant. And here's the thing about these functions, Kinsey. Another thing is that what was tucked in the back of my pre-calculus textbook for years and years didn't really emerge into relevance until earlier this year. And the point I'm trying to make here is that what we learn in this class and in your other classes perhaps, you don't know when that thing will be usable. And so what you're doing, you're building that toolbox, that analytical toolbox that is going to be able to hone in on stuff like this and be able to figure things out. Okay, then in quick, I don't want to go over much of this, the attributes. You can just sketch it. It has a domain and range. Domain, is this odd or even? It's neither. Let me just do a couple of these quickly. Domain, negative infinity, infinity, range, -1 to, or 0, excuse me, I said negative infinity. 0 to 1, right? 0 to 1. Boundedness, right? Bounded. It's just bounded, right? Above and below. And the horizontal asymptotes, does it have horizontal asymptotes? Yes. It has y equals 0, y equals 1, and limit as x approaches infinity of f of x is equal to 1. Limit as x approaches negative infinity of f of x, good job, 0, equals 0. So we'll just leave it there, okay? And now these are the basic, we've gone over the basic functions of precalculus, but I added a few others I want to go to just really quickly to glance at them. And the reason I put them here is because they have utility. You have the constant function, f of x equals x to the 0 power. And really that's just a horizontal line. And you can have a coefficient in front. If you have f of x equals 3x to the 0 power, what does that look like? Well, it's going to be a horizontal line right up here at y equals 3. So that's one thing you have. Is this an odd or an even function? Even, right? And again, this 0 is an even number. So that's all I want to say about that one. Next, the inverse squared function. So 1 over x squared. What's 1 over x squared? That's x to what power? Somebody besides Will. It's x to what power? Negative 2, very good. Okay. I told Will to be quiet, but we couldn't stop greatness happening in the classroom. Good job. All right. Yes. Is this one an even or an odd function? Or neither? Even. Okay, I don't want to say much more about this one since I added it, but can you think of a real world use of this one right here?
Launching a rock.
Similar, kind of.
Looks like a tree.
Looks, yeah, kind of tree shaped. Yeah, it does, like the trunk and all that. And I know that we're kind of smiling when Angel says that, but really a lot of these things we can just use for the pure geometry of them, right?
It could be when a plane takes off and it goes up.
Yeah. Well, what happens is gravity. Do you know how gravity force is calculated? Have anybody done physics yet? Okay. Gravity has an inverse squared relationship, that the farther away it's fractional squared as you have. So as the moon gets farther away from Earth, the force of gravity declines in this sort of a pattern. And so I specifically put this in here because of real world application. Okay, I don't want to put anything more about that. And the last one I want to look at is this one right here, the cube root of x. So how do this right here is going to be x to what power?
-3.
Okay, it's going to be to the 1/3 power. It's called a fractional exponent. So we have a radical form and a rational form of function here. And basically I put it here because it's an inverse function of a cube root function, of a cubic function. So the cubic function looks like this, right? Man, I drew it pretty well in 5th period too. It's hard to do. But anyway, we're going to use that sum, has domain and range, all real numbers. So anyway, that's that. So anyway, that's all your notes, but we're going to have one more activity planned for class, and it's this one right here. And basically this is for use of your calculator, and you're going to be matching the equation with, the picture, yes, graph. So I need you to get out your calculators and tell me whatever you have problems with, I want to show you how to do up here, because I know you're going to have some questions. So I'm more interested in you being able to do this on a calculator than I am even you being able to match these. Questions on these?
You just want us to write the letters underneath them?
I want you to write the letters, but I want you to be able to graph them. What's that? E? Okay, E, we talked a little bit about yesterday as Euler's number, but I want to show you, your question is how to graph that, right?
Yeah.
There are a couple of different ways to do it. One thing you can do is you can press second division sign, and then you could put to the power of x up here, right? Another thing you could do is you can go second natural logarithm right here, and you'll get this.
Which one?
I'll show it again. Second natural logarithm. Second and that one. Good question. Good question. Yes? Okay, sine and cosine. That's another good question. Okay, sine, what you do is, sine is right here, and cosine. So sine would be right like this. So sine x. One thing you got to think about too is what mode this is a trigonometric function. You got to think of what mode your calculator's in. In my case, it's in radians. So this is what the sine function looks like. Did that answer your question for you, Carmen? Okay.
How do you change the mode?
Okay, next question. That's another good question. Right here, Hannah, look at this. Mode right here.
Well, which one do you change? Oh, right,
Yeah, radian degree. So you'll see down here radians and degrees. You can switch. And when you're graphing a trigonometric function, you want to be in radians. Okay.
Teachers, please excuse the interruption. The teacher portal is now up, but check your email before you open it. Thank you.
Any other questions?
Again, one.
Did they make it radian?
No, they should match fine. They should match. There shouldn't be more than one. I think it should be just each for each one. Any questions on the other ones?
How do you do
K, okay, let's look at K. Very good, let's go to here. Well, look at the calculator right here. And there are a couple different ways to get to K. Probably the easiest way is to go to math and then go over here to number, and then you get down to 5, INT, see that? And so now you put like x plus 1 or whatever that is. So x plus 1.
What do you do?
Graph. Do you need to see it again? So I'm going to clear this out here. Math, number, 5. Well, I'm glad you asked the questions. Anything else you don't see? Which one is J? Let me see what J is. I didn't catch that.
Negative square root of
Oh, negative square root. So it's negative square root of x? Yeah. So here's your negative, and then here's your square root.
How do we get to E?
Second.
Second to 5.
So here's your negative square root. You got that now? Kaylee or anybody, you got that now? Negative square root? You didn't get it? Let me clear out and show you again. So I've cleared out here. I'm going to negative. You press second squared. And then you,
Yeah, but that's what I did. And then I'm graph.
2 times 4 divided
Error?
by 8.
okay. One thing you need to do is put this negative sign instead of the minus. Will that fix it for you?
That's what I did.
Yeah, try that, see if that works. Sometimes that works. So again, the main thing for this is just the calculator exercise aspect of it. And some of these we'll get back to later on. And so what we're doing with these parent functions is we're gradually going to cycle through most of them during the year.
We give this to you?
Yeah, that'll be fine.